last video, we looked at our second law of thermodynamics, and our second law told us for any spontaneous reaction, our total entropy increases, right? If it increases, then it's going to be greater than zero, right? Entropy final is going to be greater than my initial entropy, so it's becoming more disordered. So for a reaction to be spontaneous, my change in entropy is going to be greater than zero. It's going to be a positive value, right? That was for a spontaneous reaction. And this was our second law of thermodynamics. That does not fit. Second law of thermodynamics. Remember that a spontaneous reaction, right, is one that occurs on its own. If you just let it sit, will that reaction occur? And we're saying, yes, it will if my total entropy increases. We do need to remember that my total entropy, however, right, is both the entropy of my reaction, right, my system, plus the entropy of my surroundings. So my chemical system could actually become more ordered, right, less disordered. The entropy could decrease as long as the surroundings become even more disordered than the reaction became ordered, if that makes sense, right? The total has to increase. It doesn't mean both parts have to increase. It's just when I add the two entropies together, it needs to be a positive value for the reaction to be spontaneous. If it was a negative value, it would be a non-spontaneous reaction. We did have an equation also to solve for the entropy of my surroundings. It's not always a real straightforward calculation, right? If we just want to know is a reaction spontaneous or not, sometimes trying to determine criteria for our surroundings is difficult, but we can relate it to the enthalpy change of my reaction, right? We had said that if I'm giving off heat energy, then that heat energy is going to my surroundings, right? Because delta H is a measure of heat energy. Energy is conserved. So if my system is losing it, then my surroundings are gaining that same amount of energy. Remember, as the temperature of a substance increases, so does its randomness. So if we put a negative sign in front of my enthalpy change in my reaction, that correlates to the entropy change of my surroundings. And then we also divided it by T to come up with that equation. So substituting, I'm just going to do a substitution here. Substituting this in for that, I get that delta S total is equal to delta S of my reaction minus delta H of my reaction divided by temperature. And I'm going to manipulate this a little bit, and I'm just going to rewrite it. I'm going to swap those two. It doesn't matter, right? If I take 2 and add 5 to it, I get 7. And if I take, what did I say? If I take 5 and then add 2 to it, I still get 7, right? It doesn't matter the order. So I'm just going to switch these. Delta H for my reaction divided by T plus delta S for my reaction. All I did is switch them. Oftentimes when I write this initially, I write it the other way. I don't always pay attention to how I'm writing it because the total is just the two added together, and it doesn't matter the order that you add them. The reason I want to switch it here is because we're going to do a quick little kind of derivation, and I need them in this order for it to make sense. So what we're going to do next is I'm going to multiply through by negative T. So when I multiply delta S total by negative T, I get negative T times delta S total. When I take negative delta H divided by T and multiply it by negative T, I actually just get delta H. And then when I multiply delta S reaction by negative T, I get negative T times delta S of my reaction. This part here We're going to give it a new name, and we're going to call that delta G. Delta G is my Gibbs free energy change, and I'll write that down in a minute. So delta G, and it's actually of our reaction. All we're doing is defining this new term. We're saying that if I was to take the negative of my temperature, multiply it by the entropy change total, and I'm going to put parentheses around this because I want to make a big deal about this negative, I get delta G for my reaction. So we're just going to do a substitution then, and I get that delta G is equal to delta H minus T delta S. They're all of the reaction. I just left it off because I don't need to differentiate anymore, right? My free energy change for my reaction, reaction, and reaction. So they're all relative to my chemical system. I've gotten rid of the surroundings out of that equation by using this. So we're essentially just defining a new term where delta G is equal to negative T delta S total. Notice that this is total and this is my reaction. So we can actually now define a spontaneous reaction based only on information about that reaction and not the surroundings, right? Remember, total includes both surroundings and system. The other thing we want to note is that the signs are going to be the opposite. So a spontaneous reaction, right? Maybe we'll do has a positive total entropy change, right? We said it needed to increase, right? That value needs to be greater than 0, so it's a positive change. But then if I go and look up here, right? If this is a positive value, if delta S is positive, I'm multiplying it by a negative in the formula, my free energy change, delta G, is going to come out to be a negative value. So a spontaneous reaction, the entropy change is going to be positive. My free energy change is going to be negative for it to be spontaneous. We're almost always going to use delta G to define spontaneous and non-spontaneous reactions. It's just easier for us to calculate because we don't need information about the surroundings anymore. It's based totally on the chemical system. Even though delta G is defined, right? If I go back up here, it is defined including information, right? Total. That was supposed to be a marker. Including information about the surroundings, right? Total system plus surroundings. Okay, so delta G, I said I would write down what it is. It's my Gibbs free energy change. So if I wanted to say it out loud, right, delta H is enthalpy change, delta S is entropy change, delta G is Gibbs free energy change. A lot of times we'll just say free energy change, but it is indicative of the entropy, right? Even though we're saying it's energy, it is indicative of that entropy. Maybe we'll even write that down here. Delta G, and again, that's reaction, is equal to negative T delta S total. So just in parentheses. If it's a negative delta G, it's going to be a spontaneous reaction. We talked about that briefly already, right? If it's spontaneous, then my value for delta S is positive. A positive times a negative gives me a negative value for delta G. If I have a positive free energy change, it is a non-spontaneous reaction. And then if delta G is equal to 0, it is at equilibrium. The opposite of a spontaneous reaction is always a non-spontaneous reaction. And if those two are occurring at the same rate, which is what happens at equilibrium, then my total change is going to be zero, right? Spontaneous in one direction, non-spontaneous in the other. And then at the same rate, they kind of cancel each other out and we end up with zero. Because I am doing that delta again, remember delta is always final minus initial. So delta G, G final minus G initial. But again, it's really defined in terms of entropy. We're just using this equation. This is a really common equation. You're going to see this in organic. Pretty much any chemistry class you ever take, you end up using the Gibbs free energy equation. That's actually the name of it. So just kind of looking at our equation again, I'm just going to rewrite it down here. So my free energy change, my enthalpy change minus my temperature multiplied by my entropy change. So delta G is essentially the maximum energy available to do work on the surroundings. If we were to define energy, and you probably did this in 150, 151, we defined energy as the ability to supply heat or do work. This is kind of the maximum of that. It does take into account both enthalpy and entropy. So something could be non-spontaneous just based on our enthalpy change, but spontaneous based on my entropy change. So even if it absorbs heat energy, right, as long as it becomes even more disordered, then those two are going to sum together to give me a negative value. And then we could do the opposite, right? We're taking into account both heat and randomness to determine the spontaneity of my reaction. And again, in a spontaneous reaction at constant temperature changes, of course, is going to change my answer a little bit because that's part of my equation. But at constant temperature and pressure, it's always going to decrease, right? My free energy will always be a negative value. Go back up to this. Will always be a negative value for it if it's spontaneous. So kind of, we could make like a little table. This is on the PowerPoint that I do post, and I like it, so I'm stealing it right from that. But we're going to make kind of our 4 scenarios. So we'll make a little table. And I'm going to have here my enthalpy change is greater than 0. So this would be an endothermic reaction. Right? It's gaining heat energy. And then here I'll have my enthalpy change less than 0. It's exothermic. So it's losing heat energy, right? My final is less than my initial. Over here, I'll have my entropy change being greater than 0. So an increase in entropy, it becomes more disordered, more random. And then if my entropy change is less than 0, right, I had a decrease in entropy, it became less disordered, less random. And then I do want that equation in view. So kind of in each box. So in my upper left, right, am I going to be spontaneous or non-spontaneous is kind of our question. So if this is a positive value, right, I'm looking at this box right now. That's a positive value, right? My enthalpy change is greater than 0. And then my entropy change is also greater than 0. Oop, I want to put a positive there, not an asterisk. So that's also a positive value. How does the sign of delta G come out? So if it's a low temperature, right? If my temperature is small, then I'm going to be subtracting a relatively small number from that positive number, and it'll come out to be positive. So at a low temperature, it's actually going to be non-spontaneous. But at high temperatures, if that temperature was a big number, then that delta S term becomes bigger, it becomes more of a factor. And now I'm subtracting a bigger number from my positive enthalpy change, and it's going to be a spontaneous reaction. So sometimes it just depends on the relative enthalpy to entropy changes, but it also depends on the temperature. So my free energy change, delta G, is going to be less than 0 at high temperatures, so spontaneous at high temperatures. And then my free energy change will be greater than 0 at low temperatures, so non-spontaneous. Just wanted to get rid of that asterisk, not the whole box. If I go over and look at this one here, so we're now in this box. So this is a negative value, right? It's exothermic, so I'm losing heat energy. My entropy change is still positive. So would I have a spontaneous reaction or a non-spontaneous reaction? Yeah, I'm taking a negative number and then I'm subtracting a positive number from it. So regardless of my temperature, my free energy change is going to be a negative value, so it's going to be spontaneous. So delta G is less than 0 at any temperature. That's an any temperature. So I think we said spontaneous at all temperatures. And then over here, remember spontaneous at high temperatures, but then non-spontaneous at low temperatures. I was going to write all of that in the box, but I just didn't leave myself enough room. I'll write it really tiny, spontaneous at high temp, and then non-spontaneous at low temperatures. Looking down in our other boxes here, let's erase these. So my lower left, I'm still looking at endothermic. So my heat energy, right, delta H, is still going to be positive, right? We're adding energy to it. It's greater than 0. And then my entropy change, it's becoming less random, so it is a negative value. So then our question is, will it be spontaneous or non-spontaneous? So if I have a positive value and then I subtract a negative value from it, it is essentially a positive and then a positive. So it's always going to be a positive value. So my free energy change is going to be greater than 0 at any temperature, right? So it is always going to be non-spontaneous at all temperatures. And then our last one, exothermic. So we're giving off heat energy, delta H is going to be negative, and then becoming less random, this is going to be negative. So this one is going to depend on temperature again, right? So I'm taking a negative number and then I'm subtracting a negative number. If that temperature is small, then it can turn out to be a negative value, right? Because that thing that it becomes, the positive, is smaller than my negative, if that making any sense whatsoever. So my free energy change is actually going to be negative, less than 0 at low temperatures. And then if that temperature term is big, then my negative delta S becomes important. So I have a negative value minus a large negative value, so essentially a negative plus a large value. My enthalpy change will be greater than 0 at high temperatures, right? So spontaneous at low temperatures. and then non-spontaneous at high temperatures. So basically enthalpy and entropy are both important, right? You could have something that was favored based on its enthalpy but disfavored based on its entropy, and then depending on my temperature, right, it could go one way or the other. Kind of an example we could use, if I have ice, right, so solid water, so ice, and then I just set it on a table at 25 degrees Celsius, it is spontaneously going to form liquid water, right? It's going to melt. So I'm going from a solid to a liquid, which means I'm going to have a positive entropy change, right? It's becoming more random. But I have to put heat energy into it. So my enthalpy change, right, it gains energy. Remember, if things lose energy, they're favored. If they gain energy, you have to put effort into it, it tends to be disfavored. So this is favored, right? Things want to become more random. This is disfavored. So both of them are positive, but at 25 degrees Celsius, overall it happens spontaneously because that temperature, if we go back up to this is a positive value. This is also a positive value, but at room temperature, right, is going to happen spontaneously because this positive entropy change, remember I'm not plugging in 25, it's 298, right? So it is a relatively large temperature. It's going to end up to be a spontaneous reaction, right? And we know that. If I was to set an ice cube on a table at 25 degrees Celsius, roughly 72 or so Fahrenheit, it's going to spontaneously melt. So temperature is a factor. If I was to change that temperature, then I'm going to change whether or not things are spontaneous or not spontaneous. So temperature is important in determining spontaneity. Right, and we got that from this table, right? Here it was spontaneous at high temperatures, non-spontaneous at low, so temperature was important. Here spontaneous at low, but non-spontaneous at high, again, temperature was important. So things can switch from spontaneous to non-spontaneous based on the temperature. And we can actually get that by setting our equation, delta G equals delta H minus T delta S, equal to 0. Remember that the opposite of a spontaneous reaction is always a non-spontaneous reaction. So if I want to figure out the temperature at which it's converting between the two, I know that delta G is equal to 0 at that point, right? Remember, delta G is equal to 0 when it's at equilibrium. So if we're switching between a spontaneous and a non-spontaneous reaction, we're at equilibrium, delta G is actually equal to 0. So I can set 0 equal to this, and then I'm going to rearrange it to solve for T. So I'm going to divide both sides. Let's rearrange it. I have delta H equal to T delta S. Right, I subtracted delta H from both sides, but then I had a negative on both sides. I just got rid of it. And then solve for T, delta H divided by delta S is equal to my temperature. So using this equation, we can actually calculate the temperature at which it switches between spontaneous and non-spontaneous, right? This is the temperature at which it's at equilibrium. So let's do an example with some numbers. So we're going to calculate the free energy change for a reaction that has an enthalpy change of negative 227 kilojoules and an entropy change of negative 309 joules per Kelvin at a temperature of 1,450 Kelvin. So I have an entropy change, I have an enthalpy change, and I have a temperature. And we're going to just use our free energy equation to solve for delta G. And then I'm also want to know a couple other things. We want to know, is it spontaneous or not? So is it spontaneous or non-spontaneous? Does it become, and by it I mean the reaction, more or less random? Or disordered, same thing, right? Not going to fit all that in there. We'll just leave it as random. And then is it endothermic or exothermic? Do you know what endothermic and exothermic mean? Because I could say, does it absorb energy or release energy? I might not actually ask endo or exothermic. I could ask it just in terms of absorption or release of energy. So do you know what those terms mean? Most people coming out of 130 or high school can tell you if it's exothermic, it's negative, but what does that actually mean, right? It means my system is losing heat energy. So be able to answer it kind of from both directions. And we can actually answer these last two questions right now, because the sign, right, on delta H is negative, exothermic, right? It's losing heat energy, it's giving it off. My surroundings are gaining that energy. And then the value on my entropy change is negative. Remember, entropy is a measure of disorder, so because it's negative, my final amount of entropy is less than my initial, so it actually became less random. To figure out if it's spontaneous or not, we actually need to solve for delta G and then look at the sign on delta G, right? If my free energy change is negative, it's spontaneous. If my free energy change is positive, it's non-spontaneous. And then be careful when plugging them in. I do have a unit issue. My enthalpy change is in kilojoules. My entropy change is joules per Kelvin. So you do need to either convert them both to joules or both to kilojoules. Since the problem didn't state, I can do either one. I am going to convert them to kilojoules. So the negative 309 joules per Kelvin will become 0.309 kilojoules per Kelvin. And then I can just plug them in. So my free energy change is equal to my enthalpy change, negative 227 kilojoules. It is kilojoules per mole. It's kind of common, unfortunately. We should go back and add it, to just leave the moles off. I actually copied this from the slides, but I do it a lot too. Sometimes it's just left off, which can be confusing. Remember, the difference between Q, total heat transfer, and my enthalpy change is the enthalpy change was specific to the number of moles, right? It's the heat of my reaction, not just heat. But it is pretty common to just leave those moles off. They are actually there. So anyway, plugging in my number for delta H, and then if your temperature wasn't already in Kelvin, do make sure you convert it to Kelvin. So if it's in Celsius, add 273 to it. This one's already in Kelvin. And then my entropy change, negative, I forgot my negative. I am converting that to kilojoules by moving my decimal place over 3 places, essentially dividing by 1,000. So then that's kilojoules per mole Kelvin. And then units, my kelvins are actually going to cancel. So we'll have kilojoules per mole minus kilojoules per mole. Just be careful with your signs when you plug everything in. Right, I have a negative value and then I'm subtracting another negative value. So just, again, be careful with signs. And I got that my free energy change was 221. I'm just looking at sig figs, I guess just 221, nothing after the decimal place, kilojoules per mole. So spontaneous or non-spontaneous? What do you guys think? Yeah, this one's non-spontaneous. Right? I have a positive value for delta G, which means I would have a negative value for my total entropy change, right? Remember that delta G was equal to temperature multiplied by my entropy change, but there was a negative sign on that. So the signs of those two are always going to be the opposite. If you go back up to that table, this is one of those scenarios where the one is negative and the other is negative, right? So they're both less than 0. So this is less than 0. This is also less than 0, so that puts us in this box. This one happens to be non-spontaneous because we have a high temperature, right? If we go back down 1,450 Kelvin, it is pretty dang hot, high temperature. So non-spontaneous. I am going to add a second part to this question. We want to know at what temperature will it become spontaneous? And then kind of a second part to that question, will it become spontaneous above or below that temperature? Because remember, when we're solving for that temperature, we're solving the temperature actually at which it's equilibrium, at which it's at equilibrium, right? It's the temperature where it's switching from one to the other. And we want to know, well, does it need to be higher than that temperature or lower than that temperature that we're about to calculate to be spontaneous? So is it spontaneous above or below that temperature? So this is where we're using that equation that we ended up deriving by setting our free energy change equal to 0 and then doing some rearranging. So I'm just going to take my values from above and plug them into this equation. So delta H, we had negative 227 kilojoules per mole. Our units do need to be the same, so I'm going to use the kilojoule version for delta S. My kilojoules per mole cancel my kilojoules per mole, and then I'm left with 1 over Kelvin, so it comes up to be Kelvin. So negative 227 divided by a negative 0.309, and I get 735 degrees Kelvin. So this is the temperature at which it switches between spontaneous and non-spontaneous. And then our question is, do I need to be below that temperature or above that temperature to be to be spontaneous? And you can answer this a couple different ways. I know if I go back up to my original problem, at a temperature higher than that number, it's non-spontaneous. So if it's non-spontaneous higher than that number, then I know it must be lower than that number to be spontaneous. So lower than 735 Kelvin, so to become spontaneous. The other way I could answer that is I could go back up to that little table we made. Way back up here now. Right? To become spontaneous, it needs to be at a low temperature. Of course, 735 Kelvin isn't really that low of a temperature. That's still pretty high. But given our values for our entropy and enthalpy change, that's where we're at as far as switching between the two.